and conservation of heritage buildings. His research, teaching, and global collaborations have shaped modern approaches to structural safety and restoration. We are pleased to welcome him to this session. He is going to deliver his lecture online. So I request all the participants, please be seated. Thank you so much.
My name is Paulo Lourenço from University of Minho, Portugal. I'm sorry I cannot join you in India, but I'm looking forward to an upcoming visit. I will share my experience regarding multi-risk reduction and assessment, particularly at urban level, and particularly related with masonry structures and earthquakes. I will start with an introduction about managing risk and the built environment. When we talk about risk, we have to talk about resilience. And what you have there is a definition of Wikipedia. And, well, resilience is about not giving up. It's about our communities continue to exist, survive, both the inhabitants, but also the social and economic functions. And of course, community resilience is very much dependent on the resilience of the built infrastructure. Now, when we talk about resilience, there's different things we can talk about, but housing is only a part of it because our infrastructure is very complex and interconnected. And often, when you have a disaster, you experience cascading failures. And so reducing the risk in only one system is not enough. And what you can see there in the presentation is that you can have different responses to a disaster. So there is a time to observe the disaster, there is a time to recover from the event, and then you can have robust systems that go back to the original condition, and you can have ductile systems that have a lower performance but are still okay. You can have adapted systems that even recover to a better condition, but you can also have systems that collapse. And this is what we have to avoid. Now, when we talk about risk and we talk about resilience, we talk about the capacity to anticipate, the capacity to cope, the capacity to recover. And this is all about risk management. And risk management is directly linked to risk governance. And so it has also to do with our societies and our policies and our governance. Now, what I see often when people talk about risk, so resilience is a lot linked to risk management, is some mix up in concepts. So normally risk in engineering, we address it as one component being hazards, and hazards can be natural and man-made. So a hazard is a source of a potential harm. Of course, some of the hazards are more or less constant in time. Some of them, be it climate change, be it deliberate human destruction, they are increasing in power, they are changing. We can also talk about vulnerability. Vulnerability has to do with weaknesses that buildings experience damage from a hazard. And here you have an example of a structure which is not robust. And so here you can see the collapse of a real structure that the central pier was lost because of scours, so because of foundation infra excavation, and then the connected decks just fall, killing the people that are in the bridge. So these are structures that we don't like as civil engineers because they are not sufficiently robust, so they are vulnerable to an extreme event. And the different issue is exposure. And so exposure has to do with the cost and what is present in the area. Can be people, infrastructure, housing, production capacities, all of it. And obviously, the way we live today, where of course we have people moving into cities very fast, And you can see that if you think, for example, about our capital is about 30% of the entire population, and of course Portugal is a relatively small country, but if you look into Greater Tokyo, this is 4 times the size of Portugal. And any disaster in terms of population, any disaster occurring there will have huge consequences. So the way we live, we are increasing exposure. Now, risk results from these different components, which is hazard, vulnerability, and exposure. So a large risk is not necessarily associated with a large hazard. So if you have large exposure and if you have very large vulnerability, the risk can be unacceptable. And from an engineering perspective, if you like to manage risk and reduce risk because it's too high, you have to address the central column, which is reducing or mitigating vulnerability. Because it's almost impossible, in most cases in engineering, to address the hazard and change it, or to change exposure. In some cases it is possible, but in most cases it is not possible. And so in engineering, we often try to address the central column, so the column being vulnerability. Okay? Now, let's talk a little bit about earthquakes and masonry. Now, earthquakes, as you can see here, they consist about a ground motion, in this case being applied in a shaking table, and the existing buildings are often very vulnerable because most of the existing buildings have been conceived for gravitational loading, for gravity, and not for extreme events, being a large flood, a large fire, a large typhoon, or a large earthquake. Normally, the materials are fragile, the construction is very heavy, the connections are inadequate, often the design and construction are inadequate, and damage and deterioration is there because the building is existing, and often there is no maintenance. Now, when we look into the causes of the losses, we can see that about 60,000 people die due to natural hazards. And most of these people, per year, 60,000 people die, and most of these people die because of earthquakes. So earthquakes are responsible for about 60% of the natural disaster deaths. And in most cases, again, about 60% is in masonry buildings. Now, it depends extensively across our globe on how much of the built heritage is made in unreinforced masonry, but grossly across the globe, we have about half of it. And so we're talking about the buildings which are most vulnerable. And here I show you some examples of collapses because of an earthquake that we were involved in Greece. And so this is a magnitude 6.3 earthquake. This earthquake, as you can see, produced a lot of damage out of plane. You can see here that the masonry is quite bad quality. So you can see that a lot of the stones are round. The mortar is seemingly quite weak. And as a consequence, here you can see that the walls have two leaves and they separate. Now, upper parts, normally they have a higher demand. So the larger displacements, larger oscillations, and when they are not well connected, they will tend to collapse, as you can see here. So these gable walls, often they collapse, falling in the street and killing people exiting the building. So many of these buildings collapse out of plane, as you can see here, because the connections are inappropriate. They often kill the people inside and the people living in the building. And we have some examples of cultural heritage buildings or existing buildings. And these are some shaking table tests. So this is basically a facade with two transverse walls subjected to an earthquake. And you can see that all of a sudden you lose everything. You kill the people inside, you kill the people outside. Now, these are some buildings in the city center of Lisbon. You can see that they are relatively tall. You can see that we lost the pier on top. This is not acceptable. This building, in fact, has been repaired and strengthening. So you can see here some steel plates that connect the timber joists inside. And also there are still some steel angles connecting the floors to the side walls. So just by doing this very simple intervention, it was possible to increase the capacity of the building 50%. And this is the same building shown from the back. And you can see that the upper part will have much larger displacements, and there's a lot of in-plane and a lot of outer-plane movement. And so the piers are vibrating outer-plane, that's why they collapse. Now, this was a very, very simple intervention measure. It was only connecting the floors. And by connecting the floors to the walls, we increased the capacity more than 50%. So here you can see a modern building failing the way we would like Mason to fail. And so here you can see a lot of diagonal cracks. All the failure is in plane. Of course, the corners and the areas next to the windows are being lost because of the in-plane movements. But this is an exceptional response because the earthquake is extremely large. As you can see, we're losing a little bit this corner. This corner is almost lost. There is a bit of damage, but the energy dissipation is very effective. And in fact, as the earthquake is so large, the way we design is not to protect the building anymore. We just want to save lives and be sure people will not die because of an earthquake. And so, basically, there are two messages that I would like to share with you at this stage. Message one is if you have vulnerable buildings made of masonry, please avoid disintegration. So be sure that the material does not fall apart. Because if it falls apart, there is no structural model that you can use. The second message is to enforce connections. So connect transverse walls into the walls, connect walls with floors, connect roof with walls, and by doing this, you are reducing the vulnerability extensively. Now, our built heritage is subjected to many hazards. Earthquake is the most killing, okay? But there are many other types of hazards. Blast, water, impact, so this is a different type of hazard. We have fires, okay? Most of the fires are caused by humans. Of course, the Notre Dame Cathedral became very famous, but these fires are recurrent. We have floods, which are recurrent across the globe. We have landslides, which are also very killing disaster, very costly disaster. And we have liquefaction that always appears in special soil conditions close, well, during an earthquake. Now, I'll show some example of applications at urban scale of the tools that we can use and what we can obtain trying to address risk mitigation and risk assessment. So normally we talk about different tools at different evaluation scales. And we can have the territorial scale, where you can see it can be the world, a country, or a city, where our tools do not need to be exact at the building scale, because we just want to have a big picture. So we want to be sure we understand how many people die, what is the cost of a disaster, but we do not care if a building is actually surviving or failing, because it's not very important, the precision. At the building scale, the precision is very important, and then we use different tools. So the tools I'm going to show you, they apply at the territorial scale. They are not good to apply at the building scale. They can help, for example, for us to decide which buildings needs better study, okay? But not to be precise at the building scale. Now, these tools allows us, for example, to obtain images like this, which are images of damage in a city because of an earthquake in this case. And again, it's not so important if the building is yellow or if it's orange or red. What is important is at the city scale level. And we use very simple tools that sometimes require we enter the buildings, other times we can use satellite or Google Maps images. But basically, we have indicators, things like, for example, the number of floors, for example, the regularity of the plan configuration, or the conservation condition. And then we have, for each of these indicator, we have a classification, which is listed in this case as A, B, C, D. And then we have a weight. And this weight is coming from either simulations or empirical observations of real disasters. In most cases, if we have earthquakes, it will come from empirical observations. And so these forms are very simple to form and very fast, allow us to estimate risk relatively in an inexpensive and fast way. And then we can obtain data or information like this, for example. For a given scale or city or neighborhood, we can, for example, estimate how many people die, how many people are homeless, how many buildings are unusable. And that's extremely important if you have a given scenario to define how many beds you need in the hospital, to need how many tents you need to find or temporary housing for the people. We can also use these tools to apply, for example, a given seismic retrofitting package, including, for example, connecting the walls, okay, or connecting the floors, and then understand and do a cost-benefit analysis like you can see here, considering also the economic and inactivity period of after the disaster. And so you can make a cost-benefit analysis that will show us as a society if the building will be, how can I say, if the building will be, if our intervention will be a cost in the long term, or if it will be a benefit in the long term. And if it's a benefit, as a society, we should do the intervention. If it is a cost, as a society, we should probably not do it or decide if the risk is unacceptable and we should put money to live an acceptable risk. But then it's a societal decision. Should we do it or not? Here you can also see the use of these tools to define evacuation routes or routes that allow the first aid to reach the place. Because if people cannot escape or if emergency services cannot go, then a lot of people will die. So by using these tools, we can define selected areas for intervention to have evacuation routes. Now, I'm going to show you now a couple of examples of multi-hazard models. And so I started with earthquakes, but of course we can see that the costs of disasters are increasing, our exposure is increasing, and the hazards will work together. And this is the result of a PhD thesis that is being currently done at the University of Minho by the student Glenda Mascari. And I showed you another definition of risk. So there's many definitions of risk in different fields of science. In engineering, we normally use the one I showed you before, hazard times exposure times vulnerability. But it's very important to understand also capacity. Because in fact, we are not only concerned about physical fragility, but also all the other dimensions, social, cultural, economical, environmental, political, plus the capacity of a society to cope and recover. And so if there's not sufficient capacity, in fact, well, this increases the risk of a society, of an urban scenario. Now, research on single hazards has advanced extensively. Multi-hazards are still emergency. They are very complex. First, they introduced different disciplines, different attitudes towards definition of hazard, definition of vulnerability, definition of exposure. I'm going to show you an example for our capital, Lisbon city centre. And I start with showing you some pictures. So, Lisbon city centre was certainly for Europe very important for earthquake engineering. So certain in different countries, earthquake first indications were planned after the earthquake. It was what we call a perfect disaster. So a very large earthquake followed by a very large tsunami, together with a big fire. The conclusion was about 30% of the population killed, 85% of the buildings destroyed. This was in the period of enlightenment in Europe, so where knowledge became more democratic, accessible to more people, and all the big philosophers of the time wrote about the disaster. In these two opposed views, the scientific approach on we were not ready, we need to know more, use the deductive method, versus the more religious vision on what Lisbon did wrong to be punished by the wrath of God. And many people, many painters draw the disaster, even though they were not there, but from the reports. And in the picture on the right, I show you another very large disaster. This was the largest disaster since the earthquake. That killed more than 700 people and destroyed many buildings because of a flood. Now, I show you a third disaster, more recent, which was a very large fire because of multiple reasons, including past interventions that made the buildings more vulnerable and made the rescue and the access to the firemen more difficult. Okay, so there was a very large destruction in the center of Lisbon. And so our city center is the area, our case study is the area that was developed after the earthquake in Lisbon. So it's an area that is recently built from the 18th century. And these are some of the large events that affected the city in the distant past. Now, we started trying to characterize properly exposure, and I will finish with this. In fact, exposure is probably the most difficult part of the risk analysis to be characterized. And our risk is extremely sensitive to exposure. So how we define the cost of human life, how we'll define the cost of interventions, of repairs, of the buildings, and of the economic functions associated to the buildings. And here I show you just, well, in a slide, what we need to do when we address multi-risk. We need to take into consideration exposure, difficult, as I said, then hazard, in this case from multiple hazards, which typically adopt different approaches, different return periods, etc. You have to define if they interact or if they do not interact. Then the vulnerability, then the losses, then put it all together. And this is an example of our results for the losses when you combine earthquakes and floods. And so it's very interesting to see that for short return periods, flood losses are very important. So they can reach up almost to 20%. For very large return periods, of course, earthquakes are extremely destructive. Earthquakes add huge costs, and floods become far less important. Now, the second example I'm showing you is our analysis on joining earthquakes and fire. In this case, it's a cascading effect. So fire ignites after the earthquake, and we take into consideration the fire ignition and the fire propagation. And these are the losses for a 5,000 years return period, and an image also of the fire spread after 15 minutes. And so we're talking about very large losses in this case. Another example I'm going to show you is in Colombia, in Cali. I'm working together with another PhD student, which is finishing his PhD thesis also next year. We focus on non-engineering, unreinforced masonry. And here you can see the approach. And so we are combining earthquake vulnerability with liquefaction vulnerability. So we have probabilistic liquefaction asset analysis. We take into consideration the vulnerability and combine this. For the earthquake vulnerability, is very similar to what I showed you, some relatively simple indicators with a certain number of weights that will provide you with some damage. For the landslide, you combine the earthquake with geotechnical characteristics and structural characteristics. And then you have scenarios like this on predicting the damage because of the combination of the two events. Now, conclusions, I'm reaching the end. I start telling that earthquakes are the most killing natural disaster. Masonry structures are the most killing building typology, so we're writing both. We do have in engineering amazing tools to assess seismic vulnerability, both at the building level and the territorial scale or territorial level. Exposure in risk analysis is often a sort of mystery and the largest source of our uncertainty. And when we consider multiple hazards, there's many challenges still today. But that's the only way we can address risk properly. Now, to introduce discussion, and again, I'm sorry I'm not there for the discussion. There are many exciting topics because what we're doing involves the society. For example, I leave you with this question. How much risk do we accept as a society? Then who should pay the cost of disasters? Because when the disaster is large, normally we all pay as taxpayers. But should this be a government insurance issue that is combined before the disaster by using also reinsurance and not putting it all in the taxpayer afterwards? Also, when you think that by putting €1, $1, we estimate in mitigation, we estimate that we save 6 times, so €6, $6. Why are we unable to convince society and politicians to mitigate the risk and have proper risk? So thank you very much again for your attention, and I will be ready to discuss any questions you may have.